Good morning, everyone. First and foremost, I would like to thank to all organizers who are in this meeting and for providing me with the opportunity to share my knowledge. And also wanted to thanks to all participants who joined this workshop. I am Raza from Pakistan and currently working at the University of Gujrat. I'm here to share my personal experience and research. My work area is focusing on mathematics and biology, particularly with the nonlinear order differential equation to understand the battle dynamics of the complex biological complex biological problem based on the variation of the parameters. So my research is focusing on that techniques that are the numerical and computational approaches are used to define the dynamics of the diseases. And further, I'm very pleasurable because this is really pleasurable moment to engage with you and discuss exciting ways in which mathematical theories can be used to solve these type of the critical challenges. So let's begin. And I request you if there will be any issue about my mic, please during the tell me. And the discussion topic is the numerical analysis for cervical cancer using stochastic Levenberg-Marquardt backpropagated technique based on the neural networks. Today discussion is about the cervical cancer and dynamics of the cervical cancer. I mean to say that numerical treatment of the cervical cancer. So here we briefly just know about the cervical cancer. Cervical cancer develops in the cervix, that is the lower part of the uterus, and opens into the vagina. So it's the biggest key factor of this disease is the human papilloma virus. And approximately there are 200 types of the human papilloma virus, in which all of them are not risky, but high risky are the human papilloma virus 16 and 18 that are mostly caused for the occurrence of this virus. And further, it's statics because according to World Health Organization report, which is updated on 5 March 2022, so it was 2024. So according to this report, cervical cancer is the fourth most common cancer in women. And further is that according to this report in 2022, there were 660,000 new cases of the cervical cancers and 350,000 deaths in 2022. And mostly is approximated that 90%, 94% are deaths are occurring just in the low and middle income countries. And further, this report is highlighted that it's having a demographic effect on the youngest women, and consequently 20% children lost their mothers due to cancer, especially cervical cancers. Further, additionally, is that it affects mostly those women who are infected with the human immunodeficiency virus. I mean, so that who are infected with this virus and having much more chances create this type of these cells. I'm to say that I am talking about the cervical cancer as compared to the general population. And further approximated that in the total cases of the cancers, mostly 5% are those cases who are affected with this human immunodeficiency virus. And here to define the prevalence rate of this disease is necessary because with the passage of time, it's going too high and badly affecting the human. So this is the briefly just statics about the cervical cancer. Next is the main agenda. How can numerical approach Levenberg-Marquardt backpropagated technique based on the neural networks contribute to solve this problem? So here I define the Levenberg-Marquardt backpropagated technique. So first we read the methodology. What we have done here, first step is that we selected the model, nonlinear order differential equations. And after selecting this model, we define the scenarios based on the variation of the parameter in which we fix some parameters and we do a variation of the some parameter. I mean to say that we simply make a scenario with some cases, and after that we generating the data set. Here I generated the data set by using the numerical methods, Adams methods, and then after generating the data points, data sets, We train these datasets to the proposed technique based on the neural networks, and after that, we receive achieve criteria. But before achieve criteria, we check some condition based on the analysis. If all the conditions are satisfied in the analysis, then we say that we obtain the desired criteria, and then we save the result. But if we does not obtain the required criteria, it means that we have to need to readjust the neural network architecture, and then again train the results and check the again all the analysis, and check that criteria is obtained and or not. So this is the methodology. Next is that cervical cancer model. Here I selected nonlinear order differential equations, which are three. And first is define the susceptible individuals, the rate of the susceptible individuals based on the time. And second is define the rate of the humans which are affected with the human papilloma virus. And third equation here define the rate of the women which are affected with human papilloma virus, but also affected with the cervical cancers. And this model is based on the initial conditions. Further is the description of the parameters which are used in the model. So first is that beta. Beta is defined the human rate, then P with substitute P define the human risk of occurring human papillomavirus infection, and further are other parameters. So all these value of the parameter are selecting from the published studies that I mentioned there here. Further, after selecting the models, what we do, we made a scenario based on the parametric values. And here I made some scenario. I have made two scenarios with in which every scenario has three cases. So here you can see that in first scenario, you can say that I fixing the value of three parameters in which beta, mu of H, and P of C. But here vary the value of this parameter, which is women's risk of occurring human papilloma virus infection. And here I just increase the value of this parameter. Firstly set 0.1, then 1.0, and then 1.6. And similarly, I made second scenario with three cases in which I fixing these values and change the value of this parameter, and this parameter is defined the women's probability of cervical cancer related deaths. So in this way, we make scenarios. We can make a lot of the scenarios. So I have made just two scenarios to define the working. Actually, main agenda of this discussion is to define that how we use the neural networks and how we implement the numerical approaches to solve these type of the problems which based on the nonlinear order differential equations. Further, after making the scenarios, we generate the data sets by using the numerical methods. So here I generate the data sets for 40 days, and here I use the step size 0.16, and further with initial conditions whose values I have taken from the published studies. And after generating the data sets, what we have to do, we train the data sets by using the proposed techniques. But first we make the neural network architecture. So here to make the neural network architecture, I selecting the data sets for 70% data sets for training, and 15% data sets for validation, and 15% data sets for testing with maximum 35 neurons. I mean, in the different cases, I selected the different neurons, but here I maximum number of the neurons is the 35. Next is that we train the data set. When we train the data sets, then we check these data sets based on the analysis. So here are some analyses. First is that arrow histogram analysis. Arrow histogram analysis is typically used to visualize the error distribution between input and output. Here input is mean that generated data set, and output refer to the trained data sets based through the proposed techniques. So here histograms especially define the error distributions. So here error distributions define with the three colors. You can see that blue colors also define the error distribution for those data who are used for the training of the models, and further green define the also error distribution for those data that are used to validate the model during the training. And third is that errors here is calculated for those data who are used for the testing of the model after the training. So here, three types of the errors distributions are defined and defined with the histograms. And here, three histogram in just one beans. So this analysis is giving the predictions that if here just few number of the beans with very small value, that is called the errors. And if these error are approaches to
Hey, Raza, sorry, it's okay if we ask you a quick question just while we're on this slide. Uh-huh. Thank you,
just
Raza. Thank you. Perhaps I'm just a bit behind, but I just missed your cervical cancer model. Can you remind
yes,
it, please? Or
okay.
is it coming?
I mean
Oh, I see. Oh,
you
okay. So these are the three equations. Uh-huh.
yes, okay.
Okay, just a second. Uh-huh.
No, can I start?
Uh-huh. Okay.
Uh,
Uh-huh. So I
Okay,
just missed them. Uh-huh.
okay.
So if you can
Uh,
do it a bit slower, please. Uh-huh.
oh,
I'm just a little bit behind. Yeah.
okay. So
Clear.
here is analysis. This actually we what we see in this analysis. In this analysis, we see these beans, which very smaller area values, which are called the errors, and errors are calculated by differentiating the targets from to the outputs. I mean to target here represented that generated data set, and outputs is trained data sets. So if there are just few beans with very small values, it means that it defines the precision of the use techniques. So here you can see that I have not added all the figures of for all cases. I just added here scenario 1 case A and scenario 1B case, because the main is that to define how we can predict the analysis and what we see in the analysis. So here are the error histogram analysis satisfy the conditions, because here are just few beans with very smaller values which are approaching to zero. So we can give the prediction that there is the very small errors, and these errors show that trained data is almost similar to the generated data sets. Further is that regression analysis. Regression analysis, when we generate the plots for regression analysis, this is also called the fitness plot. In this plots, we check the fitness of the data. What mean is that here firstly I would like to define that what is R. R is define the correlation coefficient. Here are the three values of the coefficient. If the coefficient value is equal to one, positive one, it means that it having best fitness of the data. Best fitness mean that trained data is best fitted on the generated data sets. And further is equal to zero, it means that having no relation. And if it's going to minus, it means that it best fit but negative fitness. So here you can see that in this figures, all the data is already fit on this. And fit line here is the blue line or red line or green line or just black line is called the line of the best fitness. Mean that at the start is this line. Y is defined here trained data set, and T is defined the trained data sets, and this equations define the linear equation between the data sets. And this on this line is the fit, and it means that it's defined the good fitness. And on this fitness is data is giving a good fitness. So it means that here is not data scattering in an other areas. Data is bed fixed on this line, and this giving the prediction about that we can use the techniques to define the dynamics of any model. So further, this is regression analysis, and further is that absolute error analysis. We also calculate the absolute error analysis by different ways, graphically and also as a sorted form of the graphically. But here I added the numerical. So you can see that in the absolute error, when we calculate absolute errors or the differentiation of the generated data set and trained data sets. So as numerically we predict that, we focus on that all the numerical values are very smaller values and almost approaches to the zero. So that's why here absolute error analysis also giving the result that the data the predicted data is almost similar to the actual data. Further is that mean square error. So mean square error, we calculate the mean square error based on the data sets which are divided for training, validation, and testing. And we also calculated the times, how many neural network take our time for giving the results. So here are all the absolute, mean square errors are given. So you can see that all the errors are very smaller errors. So this result is also beneficial to satisfy that the use technique is convergent and accurate. And I'm interested in this error analysis defines the accuracy of the technique based on the neural networks. Further is that dynamics. Further, after performing the analysis, we discussed the dynamic. After defining the analysis, when we generated the data sets and trained the data set, we analyze some analysis. We investigate some condition based on the analysis. When all of these conditions are satisfied, then we define the dynamics of the diseases of any model. So here is the dynamics mechanism of the cervical cancer model. So first is that parameter women risks of occurring human papilloma virus infection. I mean to say that when I make a scenario, in the first scenario, I vary the value of the human risk of occurring human papilloma virus infection, in which I increase the value. First, I selected the 0.1, then 1.0, 1.6. So you can see that here blue is defined the case first, and also green defined the second case, and third is defined the red color defined the third case. So what is the here dynamical study of this disease? When here we investigate when we increase the value of the parameter, what it affect on the variables. I mean to say that what it affect on this class and after other classes. So here we know that when we increase the parametric value, it's the responses that individual susceptibles are going to be decreased in the populations. I mean to say that it having inversely proportional relation with these parameters. And further is that when we increase the parametric values, and this parameter is having a directly proportional relation with this class, and this class is defined that women's individuals who are infected with the human papilloma virus. And also here we discuss this class. So what is the weightage of this class? So this is prediction for 40 days. And when we increase the value of this parameter, we can see that it's also having directly proportion with this class. Actually, we used different type of the theories to find the dynamics. So here is that I am using the numerical approaches to define this approach. So here you can see that when we increase the value of this parameter, what it affect on the whole models. And further is that dynamical mechanism of cervical cancer model with the respect to the woman's probability of cervical cancer related to death. So here this parameter is highlighted that when we increase the value of parameter, I mean to say that when cancer related deaths are occurring much more in the society, in the population, so it having a directly proportional relation with the, this class susceptible class. And further is that when this parameter is increasing, the number of the number of the individuals who are already infected with human papilloma virus are going to be decreased. And further is that this parameter when going to be increased, it's also having impact on this class, which define that individuals are infected with the human papilloma virus and also infected with the cancer related. So this is here defining that this parameter having directly proportional relation this with this class. Further is summary. In the summary, I simply say that we firstly, when generated the data sets and trained based on the neural network, so we define the relationship between the output and target mean that generated data sets and trained data sets, and investigate. We have done this investigation based on some analysis which highlight that the approach is having accuracy and is convergent, and also we define its reliability. So we can use this technique to define the dynamics of this disease. And second point is highlight that when we vary the value of the parameter human's risk of occurring human papillomavirus infection, it having a directly proportional relation with the individuals who are infected with the human papillomavirus, and also with third class who are referring to the individuals who are infected with the human papillomavirus and also affected with the cervical cancers, but having the inversely proportional relation with the first class, that is showing that the size of the susceptible individual class. And third point is also defined that the prediction that we have done for the 40 days were based on the neural networks indicate that if we continuously increase the value of the parameter, I mean to say that if the probability of the cervical cancer related deaths among the women going to be increased, it means that it can affect the other classes, but it having the directly proportional relation with susceptible class and inversely proportional relation with other classes. So these are the dynamics that I defined using these techniques. And further, these are the reference where I collected all collected data. And thank you so much. And no, I want to say that if you have any questions, please feel free.